Assalamu alaikum. So today we'll be talking about logistic regression as a prelude to neural networks, and this is going to be a very important lecture. So I suggest you carefully listen to it, and maybe you'll have to listen to this lecture a couple of times. Okay, so without further ado, let me share my screen with you. Okay, I hope my screen is visible to all of you. As I said, today's topic is going to be logistic regression. So, what is logistic regression? It is a discriminative classifier for differentiating between two classes of documents using their features. So, I'm going to write that definition down. Okay, logistic regression is a discriminative classifier for differentiating between two classes of documents. And when we are talking about exactly two classes, this would specifically be known as the binomial logistic regression, or the binomial version of the logistic regression. And we'll be using their features. That is the features of the documents. So logistic regression, as I mentioned, has a very close relationship with neural networks, and neural networks can just be considered as a series of logistic regression classifiers stacked on top of each other or in different configurations. Okay? So what's because earlier we have been using naive Bayes to calculate or differentiate between regression between documents. So in naive Bayes, what we have been doing, we have been saying, let's say there are two classes and we want the predicted class. We have been doing argmax, the probability of this document D belonging to class C multiplied by the prior of class C. See? So here, what we were doing, we were taking the document and taking out its features. So we were saying this document can be represented as different features, feature 1, feature 2, all the way to feature M. And these would be the features of this document. And then we were trying to calculate this likelihood probability. Then we computed the priors, and we got through argmax the best class from amongst the two classes. So the idea behind logistic regression is that why do go through all of this when you're actually trying to predict what you're trying to predict is the class given the document. So why not just do this directly? So basically, logistic regression says we are going to predict the class C given the features of the document. See? So how does that do it? So let me show you the same using this graph. So let's say you have these documents. You have documents of class, let's say class 1, and they're distributed in the space like this according to features. So let's say this is feature 1 and this is feature 2. So you have the other documents as well. See? So you have two types of documents, and now you want to differentiate between these two documents. So what naive Bayes was saying is that you pick a document. For example, you take this document, you take its features, and you compute for each feature the probability of that feature existing in a particular class. And then you do this for all the features, and then you multiply it with the probability for a particular class, and then you do the same for the other class, and whichever probability is higher, you assign this document to that class. So contrary to that, logistic regression model says, okay, why not learn a function in this feature space? So if we can map the features onto a real space, then why not have learn a function like this, a linear function? So all of these that I'm showing you here are linear functions. So this can be a linear function, this can be a linear function, this can be a linear function. They can be even more. So let's say our regressor is trained and it learns this linear function. What it would say is that anything above this function is going to get class 1. So class 1 objects are labeled as X, and class 2 objects are labeled as circles. So anything above this line would be class 1, anything below this line would be class 2. So which means okay, this would be classified incorrectly and this would be classified incorrectly. Otherwise, all the other documents would be classified correctly. So this is the main idea behind logistic regression as compared to naive Bayes, which looks at each document separately and trains. However, logistic regression, it learns this function that differentiates between the two classes. Okay? And that brings us to the to sigmoid. Why is sigmoid important? Consider that the document D, let's say, can be represented by a vector of features. And let's say we can represent D using this vector of features x1, x2, all the way to xm. And since we have our training and test data, this document would be labeled with some class. So let's say okay, we have a set of classes and we have class 0 and class 1. So let's say okay, this document is labeled with class label is class 1. Right? And this true label would be called Y. Now, what we want using Sigmoid in our logistic regression is that we want to train probability P to decide between positive sentiment if you are doing sentiment analysis and negative sentiment. So this is a versus negative sentiment. In that case, these classes, let's say this 0 would imply negative sentiment and 1 would imply positive sentiment. So this document would be labeled with a 1. See? So the probability of Y being 1, that is this given this document D, what is the probability of this document D belonging to the positive class? See? So this is the probability of this document D belonging to the positive class. See? And hence, the probability of y being 0 would mean the probability of D belonging to the negative class. See? And then we train a function for this purpose. And let's call it Z. So this Z would multiply all the x's, all the features of the document with some weight and sum them all over and then add a bias to it, B. So essentially, what is happening here is that we take a document D, we split it into its features x1, x2, all the way to, let's say, xm. So this is that document. And what we do is that we multiply each one of these with a weight. So W1, W2, Wm. And then we say, okay, there is this bias 1 and we have this B. Then we sum these all together. So basically, x is being multiplied by w1, x1, x2 is being multiplied by w2, xm with the wm, and b multiplied by 1. And then we say, let's sum all of these up together. And we get a value, which is this function z. But the thing is, if we are looking at probabilities, nothing forces this z to be between 0 and 1. So that's where we need the sigmoid. So what is this sigmoid? This so we pass z through the sigmoid function. Okay. The sigmoid function is also known as the logistic function. See? So this sigmoid looks like this: logistic function, or the sigmoid, is basically y equals the sigmoid of z, and that is equal to 1 over 1 plus e to the power minus z. So in essence, this sigmoid function would look like this. So if you have the let me do this properly. So now I've learned this. This is the x-axis. You have the y-axis, and the sigmoid function looks like, so this is the 1, this is 0. Oh, I need to close this off. 0. The sigmoid function looks like an S. So it looks like an S. It goes like this. It never touches 0, never touches 1, crosses the y-axis at 0.5. Okay. So what this does, if I say I put z on the x-axis, it converts every number or everything generated by z, by this function z, to in between 1 and 0. So if it's z gives you a very large number, it's going to be converted to something very close to 1, 0.99. If it gives you a very small number, it's going to be converted to something very close to 0, but not exactly 0. So this is what the sigmoid or the logistic function is. It maps the values of z onto a range of 0 to 1. So that's how the outlier values are distinguishable. So what we are doing, we take z and we pass this through the sigmoid. and we get values in the range of 0 to 1. See? So that's the sigmoid. That means, okay, now we have the probability. We can say, okay, this is the probability of y being 1. See? For this document D, which has been converted into its features. So how do we convert this sigmoid to probability? So okay, probability is between 0 and 1, and now we have through the sigmoid the value of z, which has been normalized between 0 and 1. Now we have the probability of y being 1 given the document, and this we have done using sigmoid over. So earlier we had this function z, which is the summation of all the features with their respective weights. So I going from 1 to, let's say, m, and b. So I can also write this as a vector. So both of these are vectors. So I can say w is a vector, x is a vector, plus b. And then we can write this sigmoid as wx. Both of these are vectors, plus this b. So this is the dot product between the two vectors. So I can write it as the dot product. And that would mean, okay, this is 1 over 1 plus e to the minus wx, w times x, and that's the dot product, plus b. Okay. Now I want to make this a probability. So I want this to be a probability, which is not true at the moment. Why? Because for this being a probability, the probability of y being 1 given the document plus the probability of y being 0 given the document should be equal to 1. So both probabilities should sum up to 1. So that's simple enough. What we are going to do is that we are going to define the probability of y belonging to or the document belonging to class 0 or the negative class uh, by being 1 minus the sigmoid of w dot product with x plus b, and that's it. So that's going to be 1 minus 1 over 1 plus e to the minus wx minus b, and we can say, okay, this is equal to e to the minus wx plus b divided by 1 plus e to the minus wx plus b. ठीक है. So how do we make a decision? Now we have converted the sigmoid values to probabilities. So how do we make a decision on the class of D? Okay, which class does this document belong to? Because now the values of these probabilities are going to lie between 0 and 1, but they're never going to be exactly 0 or 1, because sigmoid never returns 1 or 0. So we are going to say, okay, we are going to predict a class y hat, just as we used to predict the class c hat. We are going to say y hat is going to be a 1 if the probability of y belonging to 1 given the document is greater than 0.5, right? And 0 otherwise. So if you recall, we had the sigmoid function like this. We are saying, okay, if this is the sigmoid, if the value lies here, we are going to say this is the positive or this document belongs to the positive class. Okay. So this is becoming interesting. Let's move on and see what this means using an example. So the example is I've taken a review as an example. So let me go back a bit and say, okay, remember that you have a training and a test set in the corpus. So you have a corpus. Let's say you have a corpus of reviews, R1, R2, and you have these reviews divided into training and test corpus. So right now, what I'm doing here, I'm taking a review from the test corpus and showing you here okay, how it would run once the logistic model has been trained. Okay. So just giving you a heads up. So let's say this is a review from the test corpus. It says it was, so it's a restaurant review saying it was okay. There was nothing special and the seating arrangement was second rate. So why was it so enjoyable? For one thing, the service was great. Another nice touch was the sauce. I loved it and you will like it too. So the review starts off as being neutral, then it goes to being negative, and then eventually ends up being positive. So how would we actually classify this review? It's a difficult thing. So I'll tell you okay, bhai, how logistic regression goes about solving this review. So first of all, we need to decide on the features of this review. So I'm going to make a list here. I'm going to go ahead and ouch. So I'm going to list some features called X. Sorry. So I have X1, X2. Let's say I have a few features X2, X3, X4, X5, X6, and I'm going to explain these features because we want to extract these features from the document. I'm going to description of each feature. So let's say X1 is the count of positive words. So we have a positive lexicon, and I say okay, the number of positive words in the document. Similarly, I have a count of negative words. I have a negative lexicon, uh, and the number of negative words in the document. I count them. Negations. Is there a negation in the document? So this is going to be a binary 0, 1. So binary feature. Uh, and I shouldn't write it like this. So 0 or 1. Let's say X4 is the count of pronouns and such features. So they can be the length of the document. Let's say exclamations. Are the exclamations in the review? So this is going to be a binary feature or 0 or 1. Then let's say I have the length of D as a feature, and let's take the log of the length. Okay. So now I'm going to give these features some values according to this document. So count of positive words. Let's look at some positive words. Enjoyable is a positive word. Great is a positive word. Nice definitely is a positive word. Loved is a positive word. Like is a positive word. So 1, 2, 3, 4, and 5. So I'm going to say the value of x1 is a 5. Okay. Let's look at the all of these together would count up into x1. Okay. So let's look at the negative words. Second rate, let's say, is a negative word. And let's say okay, even okay is a negative word. So I have x2. So I put down 2 for the negative lexicon. Are there any negations? Nothing is a negation. Seating arrangement. So for one thing, another nice touch. No. So this would be a 1. Nothing. So this is x3. Anyway, there is, I've said negation is binary, so it's going to be a 1 anyway. Count of pronouns. Mm, so pronouns are, let me recolor it. So I is a pronoun, you is a pronoun, and okay, that's it. So the number of pronouns is 2. Exclamations, yes, there is an exclamation. So this goes into x5, and this is a binary. So this is a 1. The length of the document, 1, 2, 3. I think it's 41. So log of 41 would be 3.71. Okay. So now we have the values of these x's for this particular review. So these are the values of the x's. So this would be the vector, the entire thing. So this would be the vector x. See? Now what we need, if you recall, for the sigmoid of, for just z, let's say we want the summation of wi uh, x of I plus the bias. Okay. So now I need wi's. So this would be, these would be trained during the training step. I'm just going to assume some values for W. Let's say the model has been trained, and these are the values for W that I have. So for W1, this is 2.5. For W2, let's say minus 5.0. For W3, it's 1 point minus 1.2. For W4, it's, let's say, 0.5. For W5, it's 2.0, and W6, let's say 0.7. And I need a B. So let's say we assume B. We're not assuming, actually. We are going to be training this, and I'm going to be talking about this a bit later, how we are going to train it. B is, let's say, 0.1 here. So right now, I was just about to tell you okay, how we're going to convert this to a probability or to a class. So what we are going to do is to figure out the probability of y belonging to class 1 given this document D, which has been converted into the features x1, x2 all the way to x6. So this is going to be the sigmoid of the vector w dot product with the vector x plus p. See, so that would be the sigmoid of 2.5 multiplied by 5 plus minus 5.0 multiplied by 2 plus minus 1.2 multiplied by 1 and all the way to B. So we have all the way to 0.7 multiplied by 3.71 plus a 0.1. So B multiplied by 1. See? So if you calculate this, this would turn out to be the sigmoid of 6.997. And you'll see, okay, if I take the sigmoid, I'll get a 0.99. So that is saying the probability of this review belonging to the positive class. So this is essentially saying the probability of this review belonging to the positive class is 0.99. And on the other hand, the probability of this review belonging to the negative class would just be 1 minus the sigmoid of the same two vectors, dot product plus b and the sigmoid taken over them. So that would be 1 minus 0.99 and it would be 0.01. See, the probability of this review belonging to the negative class, if we just have two classes, is very, very small. Right? That's what this is saying. So this is where I'm just showing you कि किस तरह से inference होती है. तो at inference time you're looking at the test set, which is here, and you are putting each review into the model given that the weights have been trained using the training set. So how are we going to train these weights? Where is W coming from? It's coming from the training on the training set, and the same thing goes for B. So these values are being all of these values actually, all of these values have been extracted from somehow from the training set. So now we are going to go and see how do we learn this logistic model and how are we going to learn these values of W and B. So the parameters of the model of the logistic regression model are the vector W and this scalar value B. So what we are given is a training set. See? So generalizing this, we are given a corpus and we have a training set of text. So text 1, and it has been labeled with either 1 or 0. To text 2 labeled 0 all the way to text n labeled 1, let's say. And I'm not looking at the test set for now. So we are just looking at the training set at training time. So we have all these text documents that are labeled. So logistic regression is again supervised method. So, and also what we are given is that y hat is going to be the sigmoid of the weight vector W multiplied by the features X plus the bias B. See? We are going to iterate over this corpus and trying to learn every time it goes over an example to see how much modification does W or B require. So this is what's happening essentially. So at each iteration, that is traversal over the training samples, we need to compute how much our model is improving by looking at training samples. And what the model would be doing is that it's going to be, so let me redraw this a bit. So I have the document T, let's say T of I, and I convert it into its features. Okay? And let's say X of N. Then before sending this to summation, I multiply each feature with some weight, right? So that's W1 for X1, W2 for X2, Wn for Xn. And then I have 1 multiplied with this bias B, and I'm computing this Z, right? Then I'm doing a sigmoid over this Z, and this is giving me a probability for Y being 1 for now, for this text T of I. See? So this text has been converted into the set of features. So what we are doing here is that we are throwing in the text, it converts it into features, then it says, okay, uh, I It goes through this logistic regression path, and it says, okay, likely this is the more likely thing I have, right? So it computes this y hat through this probability. So I get this y hat out, and now I also know, okay, what is the real y. See? So I can measure the difference between y and y hat. See? So one way of doing it is computing the loss. What's the loss? And then I'm going to say, okay, I'm going to compare. I have the real y here. I'm going to compare these two and say, okay, if there is a difference, then I need to go back and tune these weights and the bias. See? And if it's okay, then I think the values are good. So that's what's happening. Now the thing is, how do we compute the difference between these two? So the easiest way of computing the difference between two values, especially if they are binary 0 and 1, so you recall that the label, every text is given as either a 1 for the positive class or a 0 for the negative class, and the difference between 0 and 1 can be measured by, let's say, uh, y hat minus y. See? So this would be the difference. Can it be said that this is the loss? So what does this mean? This means that if my system predicted a 0 and the actual value was a 1, so the difference would be a minus 1. And what if my system predicted a 0 and the actual was also 0? So this would be 0. If my system predicted a 1, the actual label for that document was also 1, so this is going to be a 0. And the other thing is, yes, if the my system predicted a 1 but the actual label was 0, this would be a 1. You see, these are the values that we are getting between in a range of -1 to 0. But the thing is, the correct, this is where our model is correct. That's a 0. And we can normalize these by saying we take the absolute of the difference, and this would also become a 1 in that case. So 1 is where you're wrong, and 0 is where you are correct, or our model is correct. Generally what we do is we take the square of this, so 1 would be still a 1, and so forth, right? So in other cases, sometimes we do this. We call this a loss function. How much loss there is. So if there is no loss, yani we are always correct. This is going to be 0. Otherwise, it's going to be high. And there is a mean squared loss, in which you take the difference between the two. You divide it by 2 to take the mean, and you uh, take the square of it. Okay? So that's a mean squared loss of sorts. But this really does not fit in. So what we really need now is a loss function that computes the loss between the predicted value and the real label. So how much y hat differs from y. And that's the essence of the loss. So that brings us to the loss that we generally use in our logistic regression classifiers. It's called the cross entropy loss. Right? So this is a special kind of a loss function. Loss function, and I'm going to tell you why we need it. That prefers the correct class labels. Say, i.e., for choosing our parameters. So recall that we want to choose our parameters W and B. So we want to choose parameters W and B, where the loss is minimum. See? So what does this mean? This means, okay, we want to maximize the probability or the log probability of the true Y labels. Okay? So thus what we want to do is to maximize the probability of this document um, X belonging to, it's, let me call it T, or the text T belonging to class Y. And recall that all the text documents in your training set are labeled. So we can see the loss. So this is the cross entropy loss, and how this is how it's computed. So this is the predicted value Y, and this is the real value in its power. So the real label of Y, and then 1 minus Y hat over, or to the power 1 minus Y. So what does this do? In fact, the previous the loss functions that we saw have a few problems, because to back propagate the loss or to take it back, we need to differentiate it, and those loss functions are non-differentiable. This is a differentiable loss function. This is going to be this is going to give you a 1 if the classifier predicts correctly. Predicts Y hat correctly. ठीक है? And how is it going to do that? So just see. Okay, if I'm getting into this difficulty. Okay, so let's say कि Y hat prediction is a 0, and Y, the real label, is also 0. So what's going to happen? So Y hat 0 to the power 0 is going to be a 1, right? And in this case, this is a 0, so 1 minus 0 is 0, and 1 minus 0 is, sorry, 1 minus 0 is a 1, and 1 minus 0 is a 1. So 1 multiplied by 1 would give you a 1. If you note, okay, if Y hat is a 1, whereas Y, the real label, is 0. So what's going to happen is that Y hat is a 1 to the power 0. This is going to be a 1 to the power 0 would be a 1, right? And 1 minus 1, right? So, sorry, 1 minus 1 would be a 0. So this would be a 0. And since the real label is 1, or sorry, 0, so this is going to be a 0 to the power 1, and this is going to bring the 0 in, and multiplied by 1 would become a 0. So this probability would be 0 if the label predicted label is incorrect. ठीक है? So what we want now is to change this to a log. So we take the log of both sides. So we take the log of the probability of Y given this document T, and we take the log of Y hat to the T 1 minus, sorry, Y hat to the power Y, and 1 minus Y hat to the power 1 minus Y. See? And when we apply the log laws, you can see that this becomes Y log Y hat, plus 1 minus y log 1 minus y hat. Okay, so this is what we have. Now, what we want is to convert this maximizing function into a minimizing function, right? So converting a maximizing function, so let's say you have a function like this, and you wanted the maximum value. Sorry. So you had, and you wanted the maximum value, convert it into a minimizing function. You just take the negation of it, and it becomes like this. So it becomes a minimizing function, not exactly to scale, but the value at which the minimum point of this minimizer is the same as where the real function was maximizing. So that means okay, the cross entropy loss that we wanted to define is actually the negation of the log probability of y given t. See? And that would be the negation of this entire function that we had above, y log y hat plus 1 minus y log of 1 minus y hat. Okay. Now, let me detail this a bit and say let's plug in the value of y hat. So we had y hat being the sigmoid of wx plus b. Okay. So we'll plug this in into the formula and say, okay, bhai, this is the negative of y, the real label, log of the sigmoid of the dot product of w and x plus b plus 1 minus y and the log of 1 minus the sigmoid of wx plus b. See? So I've just plugged in this value of y hat, which was the expected probability, into the into this loss function, into the cross entropy loss function. See? But the thing is, okay, these are for the. So before I go on to the cost function, these are for a single example. So if you recall, in our training set, just the training set, we have several examples. We have T1 with some y, T2 with some other y, and so forth. And we have Tn with some y. So these are the real labels y. Now I want uh, the log. So what would be the log of the probability over the entire training set T? So let's call this entire training set T. Okay? That would be the log of uh, the multiple of these probabilities for each y of I. So this in this case would be y of 1, and this would be y of 2, and so forth, uh, given the text document I. Okay? And this would go from all the way from I equals 1 to n in this case. Okay? So when we move the log inside the product, that would become a summation, and that would be the log of the probability, the same probability, y of I given t of I. So this is for the entire function. If you recall, this was the negation of the cross entropy loss. So this would become the negative sum of the cross entropy function that we had for y hat of I, and this would be y of I and this is the difference. So I equals 1 all the way to n. Now, since we have the cross entropy loss, what we want is a cost function that we really want to minimize. Okay. So what's the cost function for this logistic regression? So now we are able to define the cost function. Now we can define the cost function in terms of the cross entropy loss for the entire training set. See? And this would be the average loss for each sample in the training set. Average means because we have n samples in our training set. So this is our training set, and we have T1 all the way to n. So we would be dividing our cross entropy loss to by n. So let me define this cost function j, and let me give these this j the parameters w, this vector w, and the scalar b, and this would be defined as the sum of the cross entropy losses for each sample y of I, and this is going from I equals 1 to n, and I just take the average. So let me open this up. So this cost function j in this case would be, when I plug in the value of the cross entropy loss from our last page, that would become minus 1 over m, the summation of y of I. So this I, sorry, so this is not an m, this is an n. So I going from 1 to n, the y of I, log of the sigmoid of the weight vector multiplied by uh, x of I plus b plus 1 minus y's of I multiplied by the log of 1 minus the sigmoid of weight vector multiplied by the ith. So these are the features of the ith sample in the training set. So this is what we have at the end, and this is the j that we would eventually want to minimize. So this is the cost. So we would, or we want to minimize the cost j for our logistic regression. So I think this is quite a bit for today's lecture. So in the next lecture, we are going to be looking at how do we apply gradient descent for minimizing uh, j. Okay. Thank you very much. I'll stop here, and if you have any questions, you may ask.